Sorry.
So today I will talk about inner variations. So the first part of my talk will be to introduce these inner variations, what they are and what can they be useful to. And then I will consider two regularity problems coming from these inner variations. In a third part, I will show that these problems are motivated from physics, actually from three physical problems. The first one is the study of vortices in Ginzburg-Landau theory, so for superconductors. It's a superconductivity subject, but not only because it's connected also to the Euler equation in incompressible fluids and to the stationary system of n-point vortices. So I will be more precise in the following. And after giving this motivation, I will try to sketch the proof of the two regularity results that I will show in the second part. So the starting point of my talks is the variations in calculus of variations. So what is calculus of variations about? We want to characterize the extrema of a functional by doing small variations. And doing so, we obtain what we call Euler-Lagrange equations. Thanks to this equation, we can hope to say something about the minimizer, the extrema of our functional. Either if we are able to solve the equation, we can describe it completely, or at least say some properties like regularity or things like that. And it goes also backward because we can solve PDEs by minimizing energy. So the object of calculus of variation is to study something more general than extrema, something which is called critical points. And for example, for a functional f defined on the Sobolev space H1, we say that H is a critical point of f if the Gato derivative of f vanishes at 0, meaning that if the derivative with respect to t of f h plus t phi is 0 for every phi which is smooth with compact support in omega. And these variations, I will call them outer variations because they modify the image of a function. We change the image of the functions. A classical example is the critical points of the Dirichlet energy. So without constraints and for real functions, the critical points of the Dirichlet energy are harmonic functions, solutions of Laplacian H equals 0 in omega. Okay, but we can make other variations. There exist other type of variations, and these are inner variations. This leads me to the definition of the stationary points. So if I have an energy, I will say that H is a stationary point of this energy if for every smooth, compactly supported vector fields, we have that the derivative with respect to t of f of h of x plus t x of x is 0. So what I do when I do that is that I change the domain of my function. I'm composing my function by a diffeomorphism of the domain. So these are inner variations, and they are like opposed to the outer variation because here I change the image, the domain, and not the image. So what do we obtain if we do inner variations with the same Dirichlet energy? So we obtain a different equation, and this equation can be written in the form divergence of something equals 0, and the something is a matrix or a tensor, 2 by 2 tensor, which is called in the literature the stress energy tensor. And this is a symmetric matrix, traceless in dimension 2. And this is exactly the derivative with respect to y of h squared minus the derivative of x of h with respect to x squared, and so on. Something which is important to observe and which will be useful in the following is that in this expression, I have square and products. This is a conservation law, because this is something which can be written in the form divergence of something equals 0. So this is what we call a conservation law. And here we find, for the same energy, for the Dirichlet energy, we find a nonlinear equation. And this nonlinearity appearing here will cause a loss of regularity and a loss of uniqueness of some solution if we impose boundary conditions. A way to see that, for example, is that in dimension 1, the stationary points of the Dirichlet energy satisfy that the norm of H prime is constant. And here we can have only Lipschitz solutions if I take a zigzag function. In the same way, we can see that we have non-uniqueness because I can construct a zigzag function with 0 boundary condition, and the only harmonic function with 0 boundary condition is 0, but I can have a zigzag function with a constant slope, which is 0 on the boundary of an interval. In dimension 2, because the matrix is symmetric and traceless, we can use complex analysis and introducing the operator partial z and partial z bar, which are defined classically as partial x plus I partial y and the conjugate with a factor 1/2, we can see that we obtain this equation tell us that something is holomorphic, the derivative with respect of z bar of something is holomorphic, and this something in the scalar case, in my talk, h will be a scalar valued function, can be written in the form partial z h square. So I have an equation like that. So again, I repeat. So the classical variation, the variations of the form h plus t phi are called outer variations. These are variations of the image of h. And the variations of the form h of x plus t of x, where x, big X, capital X is a vector field, are called inner variations. They are variation of the domain. Of course, these two types of variations are related. So we will see now how they are related. First, the link between these two notions is regularity. What I mean by that is that we can see that if h is a critical point for a functional f, and if h is regular enough, here C2 will be sufficient, then h is also a stationary point. A way to see that is to use Taylor formula, which is allowed by the regularity. So we write an inner variation as an outer variation thanks to a Taylor formula. Conversely, if h is a stationary point and h is regular enough, here also C2 will be sufficient in general, but sometimes we can ask less, sometimes more. Then we have an alternative. Either h is constant or h is a critical point of f. And this fact was, I think, more or less known in the literature, but there is a nice paper of Alikakos and Faliagas which states it very, very clearly. And a proof of that in the case of a Dirichlet energy is the following. So in dimension 2, I will use complex analysis, and we have seen that the divergence of a stress energy tensor equals 0 can be written with the operator partial z bar and partial z. I will use the chain rule, and I am allowed to do that because h is smooth enough. So I will find that this equation implies that 2 times the second derivative with respect to z and z bar of h times the partial derivative of z of h equals 0. And this is exactly that the Laplacian of h times the gradient of h equals 0. So then once I have this relation, I can discuss, and we can see that either the gradient of h is 0 or the Laplacian of h is 0. And with a little bit of work, we can see that either h is constant or h is harmonic. Okay, but even if these two notions are very related, there exists stationary points which are not critical points and critical points which are not stationary. So the example of critical points which are not stationary, I mean, the one I know is from Tristan Rivière, who constructed harmonic maps into sphere, which is everywhere discontinuous. So it cannot be stationary harmonic, because we know from regularity results of events and virtual that if it were stationary harmonic, then it would have a partial regularity. So this shows the example of harmonic maps. Here, harmonic means harmonic into manifolds, which are not stationary. And conversely, there exist stationary points which are not critical points. We have seen them in 1D, for example, the zigzag functions with constant slope. They are stationary harmonic, but they are not harmonic because harmonic functions are just affine functions in dimension 1. I would like to advertise a little bit these variations. So why are they useful? So first, these are kind of natural variations in nonlinear elasticity. So in nonlinear elasticity, we usually work with a constraint that the Jacobian of U is positive almost everywhere, because this means that we want to prevent interpenetration of matter. And when we do outer variations, this condition is lost. However, if we do inner variations, then this condition is preserved. And more generally, inner variations preserve the homotopy class in which we work. And so these are kind of natural variations. Another reason to advertise the variation is that they are relatively not well known. And I will quote Ivanets, Sobolev, and Oninen, which wrote in a paper of them that their study is still in its infancy. There is a huge literature on regularity theories for outer variations, but there are relatively few results on inner variations. And so I mentioned the work of Ivanets, Sobolev, and Oninen. They studied vectorial problems. In my talk, I will focus on scalar problems, but in dimension 2, they studied the vectorial problems, and under some conditions, they proved that inner variations lead to Lipschitz regularity. And another well-known example where the stationarity is used is the work of Evans and Betuel about the regularity of stationary harmonic maps. So here the word stationary means stationary and critical. They used the both equations to deduce regularity. Although they are not well known, this variation, they are responsible for two tools which are very useful in elliptic and in regularity theory. The first tool is the monotonicity formula. When we have inner variations, we can derive the monotonicity formula, and we can also derive Pose-AF formula. Pose-AF formulas are useful to prove, for example, non-existence of some class of solution of elliptic PD. So now I will state my problem or my problems, because I will consider two problems. I will focus about the first one, which is related to stationary harmonic function. So the problem is the following. I give myself a smooth bounded domain, and I consider the set of Radon measure in this domain. So for me, a measure can be signs. It is not necessarily a non-negative measure. And I ask the following question. What are the function h in h1 and the measure mu, which satisfy Laplacian of h equals mu and some quantity that I call omega of h, which is partial of xh squared minus partial of yh squared minus 2i partial h with respect to x, partial h with respect to y. If I ask that it is holomorphic, what can I say about the regularity of h and the regularity of mu? So the problem is to study the inner variation with the supplementary hypothesis that the Laplacian of h is the measure. And this measure is particularly interesting from the physical point of view, because we will see in the following that it will tell us where the vortices in superconductivity will place in the superconductors. So the question is really, what does the support of mu look like? It can be curves, it can be set. I mean, we ask the question, can it be a curve? Can it be a set of full 2D Lebesgue measure? Can it be something else? And again, the fact that the quantity omega h is holomorphic is that it's only to say that it's just to say that h is stationary harmonic, meaning that it is stationary for the Dirichlet energy. So this quantity omega h, it is reminiscent of Hopf differential. So the Hopf differential for me, it's when h is vector valued. Here h is a scalar valued, but it has exactly the same form. So we start with giving some examples on function which satisfies the two conditions I have given. So first, from what I said at the beginning, we can see that every harmonic function is stationary harmonic. Why? Because a harmonic function is smooth. It is a critical point, and a smooth critical point is also a stationary point. And in this case, the measure mu is 0. So this is the trivial example. The second example is when I take the absolute value of a harmonic function. So I take h, the absolute value of a harmonic function. I suppose that my harmonic function changes sign. Then I can see that little h satisfies my condition. And I can see that the support of a measure is actually the set of 0 of h. So how can I see that? This is because so first, little h is stationary harmonic because the gradient of the absolute value of capital H is plus or minus the gradient of capital H. But in the stress energy tensor, they are only quadratic expressions. So the stress energy tensor doesn't see sign. So if capital H is stationary harmonic, then little h will be stationary harmonic. And that's why little h is stationary harmonic. And then why the measure of mu is supported on the set of 0 of h. So this is a computation in the sense of distribution. So I compute the Laplacian of the absolute value of capital H. For that, I used that capital H is in H1. I divide my domain in the part where H is non-negative and the part where H is negative. I used an integration by parts, and the boundary of these two domains are the same, but the normal comes with an opposite sign. So at the end of the day, I find the integral over the 0 set of H of the normal derivative of capital H times phi. So I can explicitly say what is capital H. And this example is good, I mean, because we know what the 0 set of a harmonic function is. We know what it looks like locally. Locally, it is either a curve of an intersection of curves, and we know this angle. I will come back to this in the following. So we have only these two examples, and my first result, which I will state in a moment, says that actually the example 2 is the only example that can arise in some sense. But before stating this result, I want to ask another problem, which is completely related, and I stated to give more example of stationary points. And the problem will be the following. What are the function h in h1 and the measure mu such that minus Laplacian h plus h equal mu, and this time the stationary equation is replaced by another equation, which I wrote also in a complex form. And instead of having the Hopf differential is equal to 0, we have that the derivative with respect to z bar of the gradient, the complex gradient of h square is 1/4 of the partial derivative respect to z of h squared. And the problem is the same to describe the regularity of h and of mu. And again, mu will give some information about the location of the vortices in superconductivity problems. And these problems comes also with boundary conditions. So we will be interested in a boundary condition. And there are two types of boundary condition. The first one is if we prescribe h equals 0 on the boundary, and the second is when we prescribe h equals 1 on the boundary. And we ask the following question: does there exist a function h satisfying my two conditions with h equals 0 on the boundary? And I'm interested in the existence of non-trivial solution. So as in the previous problem, I will give example just to give many examples of stationary points of functional. And I didn't say, but here the second equation means that h is stationary for the Sobolev norm, meaning for the Dirichlet energy plus the integral on omega of h squared. So this equation means exactly that h is a stationary point for a functional, and this functional is the Sobolev norm. So the first example is, as before, the critical point, meaning that if h satisfies minus Laplacian of h plus h equals 0, then h is stationary. Why? Because then it will be smooth by regularity theory, and we have seen that a critical point is also a stationary point if it is smooth. So this is also the trivial example when mu equals 0. And the first non-trivial example is given by a classical problem in calculus of variation. This is the obstacle problem, but the obstacle problem with a constant obstacle. So I give myself a number, positive number lambda, and I call h star the unique minimizer of the obstacle problem. So the minimizer of f of u, here f is the Sobolev norm. So I repeat the Dirichlet energy plus the integral of u squared. I minimize this energy, this functional, under a prescribed boundary condition. I ask the function to be 1 on the boundary, constant equal to 1 on the boundary, and I ask the function to stay above an obstacle, constant obstacle, which is here 1 minus 1 over 2 lambda. So if I have a unique minimizer of this problem. Why? Because the Sobolev norm is strictly convex, and I minimize a convex function in a convex set. And I pretend that this unique minimizer is stationary for the Sobolev norm. So it satisfies the equation I've seen before. Why? Because when I do inner variation, I stay in my admissible test function. I stayed in the minimizing space. The inner variation leaves this space invariant. And here it is very important that the obstacle is constant. So from the regularity theory of the obstacle problem, I know that the unique minimizer of the obstacle problem is C11. And this is due to Frese and later Clafarelli. I know also something about the regularity of the free boundary. And in this case, I can describe mu because I have at minus Laplacian of h star plus h star is equal to 1 minus 1 over 2 lambda times the indicatrix function of the set where the gradient of h star vanishes, which can be rewritten as h star times the indicatrix function of the gradient of h star equals 0. And in this case, this is not only a measure, but this is also an L infinity function. So my first non-trivial example is something which is quite regular because it is C11, and the measure is an L infinity function. But there are examples which are less regular, actually, which have the same regularity as for the stationary harmonic problem. And for that, I can cook up an example starting from a 1D problem. So in 1D, I take a function which depends only on one variable, let's say x, and I take an increasing exponential until x equals 0, and then a decreasing exponential. Then if I compute the derivative in the sense of distribution of this function in 1D, I will have a Dirac at 0. And if I consider this function as a 2D function, then the measure will be supported on the line x equals 0. And again, this function can be shown to be stationary. And what is the regularity? It is Lipschitz, locally Lipschitz, and the measure is concentrated on a curve. So these are the 3 examples for the second problem. And my second result, the second result I want to state today is that these examples are, in a way, the only ones for the regularity problem I presented. So now let me state precisely the first regularity result. So a regularity result for the first problem, the problem of stationary harmonic function with Laplacian, which is a measure. So if I take h and mu, which satisfy my condition, then first the critical point of h are isolated. And if I take a point in the support of mu, which is not a critical point, I can assume, because the problem is translation invariant, that h of 0 is 0. And in a neighborhood of this point, I will find a harmonic function capital H such that I can write h equal absolute value of h in this neighborhood. And this is up to a sign, because I can h as a sign, so I can reverse the sign. And also, this shows me that the support of a measure, mu, is the 0 set of capital H, the harmonic function I have found. So this result tells me that locally, near regular points, the example I show for the stationary harmonic maps are the only ones. In the same way, for the problem, which I call a problem with magnetic field, so the problem for stationary point for the Sobolev norm, I have some regularity result, and this says the following. First, the support of the measure intersected with the set of points, with a set of regular points of h, is locally h1 rectifiable, and I can describe mu. There exists a sine function, which I call sigma, such that mu is equal to h times the indicatrix function of a set where h is 0, of a set where the gradient of h is 0, plus 2 times the sine function times a measure which is supported on a line. And again, the first part in this theorem corresponds to the obstacle problem example, and the second part corresponds to the exponential I showed, the less regular part. So in a way, it states that the example I showed are the only ones which solve the equation I have introduced. Part of the regularity result is that h is constant on the connected component of the support, and this is important in superconductivity because h corresponds to a magnetic field, and mu corresponds to the location of the vortices. So it says that the magnetic field does not penetrate in through vortices. And I also mentioned a boundary problem. So I will show uniqueness results and for smooth bonded and star-shaped domain. So if H is a stationary point for the Sobolev norm, and if H is 0 on the boundary, then H is necessarily 0. And the word star-shaped makes think of the Sobolev formula, and this is what I will use because I have a stationary point and hence a Sobolev formula to prove the uniqueness result.
A short question.
Yes.
Is this in 2D or in any dimension?
Everything is in 2D.
Okay.
everything is in 2D. For me, omega is a 2D domain and everything is in 2D. All my talk will be for 2D domains and for scalar valued function. So now I go to motivation. And so my first motivation was the Ginzburg-Landau model in superconductivity, and I will present it. I will present the case without magnetic field, maybe because it is simpler to write. So in superconductivity, without magnetic field, we want to minimize or find critical points of the Ginzburg-Landau energy, which is the Dirichlet energy plus a potential part, which is 1 over 4 epsilon squared times the integral over omega of 1 minus u squared. And this part penalizes the set where u is far away from 1, the zero set of u. So when epsilon tends to 0, u will tend to something of modulus 1, except in small region of size epsilon, which we call vortices. So u in this model is a wave function. So with the normalization I used, u is less than 1. And this is a phase transition problems. So the phase where modulus of u is close to 1 is the superconductor phase. And the phase where the modulus of u is almost 0 is the normal phase. And the game is to understand the location of the normal phase and of the superconductor phase. So from what I said, we see that in the limit epsilon goes to 0, the sample will be almost everywhere in a superconductor phase, except on points which we call vortices. So this model has been studied after the pioneer work of Bétuel-Brédis-Sénin. And the main feature of this model is that it describes the appearance of vortices. So what are vortices? These are regions where the modulus of u is close to 0, let's say equals 0, and around which u has a non-zero degree. So what is a degree of a vortex? So this is the change of a phase. This is an integer which measures the algebraic change of the phase of u. So if I write u equals rho times ei phi, which I can do near my point, then the degree is the integral on the boundary of a ball, not on the ball, of the tangential derivative of the phase. And here we see in the figure vortices appearing in a superconductors, and we see that they arrange themselves in a lattice, which is a triangular lattice. And the mathematical theory in Ginzburg-Landau is built to understand the appearance of this. I mean, the main goal is to understand the appearance of this Abrikosov lattice. Okay, and now I will be interested in critical points, not in minimizers, but in critical points of the Ginzburg-Landau energy. And I will consider critical points in a smooth, simply connected domain. I consider a family of solutions. So critical points of the Ginzburg-Landau are solutions of the Euler-Lagrange equation. I wrote here the Euler-Lagrange equations. We assume that the modulus of u is less than 1. With some boundary conditions, this can be shown through the maximum principle. And we assume that we have some bound on the energy. So the energy is not too large, meaning that this is 1 over epsilon to some power, and the power is less than 1/3. Okay, how can we describe the zero set of u if there are an infinite numbers of these zeros? The answer is that we will describe them through a vorticity measure. And to introduce the vorticity measure, I need to introduce the superconducting current, J epsilon, which is the inner product between IU and gradient of u. And I take the rotational of J epsilon, which I call mu epsilon. By using the Euler-Lagrange equation, I can see that the divergence of a superconducting current is 0. And hence, because I work in a simply connected domain, I can use Poincaré lemma to write J epsilon as a gradient perp of some function, which I call H epsilon. mu is given by the rotational of a superconducting current. So if I take the rotational in this relation, what I find is that the Laplacian of H is equal to mu epsilon. And here yes.
Sorry, Remy. One quick question. This I u epsilon, the I is a rotation, or what is the I?
I is the multiplication by the complex number I.
Okay, so okay. Thanks.
Yes. So J is a vector. And component-wise is like u epsilon, the determinant of u epsilon times the derivative with respect to x of u epsilon. This is the first component, and the second component is u epsilon, determinant of u epsilon, and the derivative with respect to y of u epsilon. So this is a vector. I can take the rotational, which gives me a scalar in two dimensions, and I find this equation, which looks like the equation I introduced in the beginning. And I want to pass to the limit when epsilon goes to 0 in this relation. So I need to have a rough description of the measure mu epsilon, and this is given by a result of Sandy and Serfati, which this result tells me that when epsilon is small, then I can write mu epsilon as a sum of Dirac masses. The sum can be very large. I mean, n epsilon, the number of vortices here are a, I epsilon, can be very large. But mu epsilon is roughly equal to this sum. And the vortices come there with their degrees. So if I want to pass to the limits, I need to have a bounded measure. So I divide by the total number of vortices, meaning that the number of vortices counted with their degrees. And I will pass to the limit. But what is the result? This is the following. So I take u epsilon as before. I need to assume also a bound, an L-infinity bound on the gradient. And I assume that the number of vortices is of the same order as the square root of the energy. And this is the most relevant case in the Ginzburg-Landau theory, when the number of vortices is of the same order of the square root of energy. Then I can divide my measure by the total number. This will give me a bounded measure. So this is equivalent to divided by the square root of energy. And I can pass to the limit. In the same way, I can show through the bound on the energy that H epsilon, if I rescale H epsilon by dividing it by the correct number, then it converges weakly in H1. And mu epsilon converges weakly in the sense of measure. I pass to the limit in the equation that I have shown before, and I have the Laplacian of H equal mu. And H is not any function. It satisfies that its Hopf differential is holomorphic. And this comes from the fact that I studied critical points, which are also stationary points of the Ginzburg-Landau energy, but I will explain that in more detail. So this theory and this theorem due to Sandy and Sarfati tells me that to study the repartition of vortices, I have to study the function h, which satisfy Laplacian of h equal mu, and which are stationary points of the Dirichlet energy. So that's why my problem, I mean, that's where my problems come from the study of vortices in a superconductor. So now I want to explain more where does this equation come from, and because solution of the Ginzburg-Landau equations are smooth through elliptic regularity theory, they are also stationary points. So I can write that they satisfy an equation of the form divergence of something equals 0 with the something equals to the stress energy tensor associated to the Ginzburg-Landau functional. And now we want to pass to the limit in this equation, not in the Euler-Lagrange equation, but in the inner variational equation. And this is another use of this inner variational equation. This is to pass to the limit in some singular limit problem. Now I will explain it a little bit hand waving. So since the modulus of u epsilon is almost equal to 1 almost everywhere, I can use the definition of H epsilon to see that the difference between the derivative of u epsilon with respect to x squared minus the derivative of y of u epsilon with respect to y squared is almost equal to the same quantity but with h. And the same for the inner product between the derivative of u epsilon. So this tensor will be roughly equal to the stress energy tensor of H epsilon. And we can see that this part of the tensor will go to 0. The problem is to pass to the limits in this kind of quadratic expression. We have only weak convergence in H1 of H epsilon. So a priori, we cannot pass to the limits in quadratic, in nonlinear expressions.
So there's a question here.
Yes.
Can you remind me again of what H epsilon is here?
So H epsilon is defined as J epsilon, the superconducting current, equals the gradient perp of H epsilon. Should I go back? H epsilon is defined here. And this plays the role of a magnetic field when there is no magnetic field. So in the case with magnetic field, you have to replace H epsilon by the true magnetic field. But it is simpler to explain the problem in the case without magnetic field. So we have to pass to the limits in these nonlinear expressions. And although we have only weak convergence in H1, Sandy and Sarfati prove that we can pass to the limit, and then we can pass to the limit in this equation, giving a criticality condition for the limiting function H. And this is reminiscent of a theorem of Delors for vortex sheets of the incompressible Euler equation. He had to pass to the limits in the same kind of expressions with only weak convergence in H1. And because of the very particular structure of these terms, it was possible. And here also, this is the very particular of this tensor, very particular form of this tensor, which allows to pass to the limit. So this is what I want to underline, that also inner variation equations can be useful to pass to the limits in some physical problem. Now I will mention briefly two other applications, or rather motivations. The first one is that there is a link with the Euler equations. Why? Because if we consider a stationary solution of the incompressible Euler equation, which is written here in this form, so these are the Euler equations in fluid mechanics, incompressible because I ask that the vector field is incompressible, meaning the divergence of V is free. Then I can define the vorticity of a fluid by taking the rotational. And the result is that if H is in H1 and mu is a random measure which satisfies the equation I have shown at the beginning, then if I define my velocity field by the gradient perp of H, this is a solution of the Euler equation with vorticity mu. So I found solution of the stationary incompressible equation with vortex sheets, and the sheets are the lines of vorticity given by the zero set of harmonic functions. And also connected to fluid mechanics and vorticity, I want to mention the stationary system of point vortices. So what is that? We say that a family of endpoints is a stationary system of endpoint vortices if they satisfy an equation which is written here. So this is a relation between the position of the points. And I give myself degrees, natural numbers, in this equation. And the question is to understand how the points will arrange when when there is an infinite number of points. So in order to do that, I define the vorticity measure mu n, which is the sum of the vortices divided by the total number of the vortices. And I can pass through the limit because this is a bounded measure. And what I can prove is that there exists in a function h such that Laplacian of h equals mu. And if we know by chance that h is in H1, then h is stationary harmonic. So the problem presented at the beginning also describes some limits of stationary system of n-point vortices, limit when the number of points goes to infinity. So these are my three motivations. So superconductivity, free mechanics, and a stationary system of point vortices. They are all connected to inner variation and stationary harmonic functions. So now I would like to give an idea of a proof of the first result I presented, that stationary harmonic functions whose Laplacian is a random measure can be written locally as the absolute value of a harmonic function. And the starting point of a proof is this identity. We can write, in the scalar case, we can write the off differential as the square of the complex gradient of h. And this identity is not true in the vectorial case. This is where I use that h is scalar value. So this can be shown just computing this. So then near a point where the gradient is not zero, then I can see from this relation that the off differential is not zero. And if it's not zero, then I can take a square root of this function, a square root in a complex sense. So I can find a sine function theta such that my complex gradient of h is equal to theta times the square root of omega. So I know that maybe I shouldn't denote the square root by this sign in the complex case, but this is really what it is. This is the square root. That's why I am using it. So in the board, we have this relation. So now what we will do is that we will integrate the square root of the off differential to find a harmonic function, capital H, such that the square root of the off differential, which is also a holomorphic function, because when I take a square root of a holomorphic function, when it is defined, it is a holomorphic function. And if I integrate and take the real part of a holomorphic function, I can find a harmonic function such that we have that the gradient of h is equal to theta times the gradient of capital H. So I see rather quickly that the gradient of little h is equal up to a sign to the gradient of capital H. And now I have to understand what is this sine function theta. And for that, I will use the information I have in my equation, meaning that the Laplacian of h is a radon measure. And using that and computing the, deriving this equation, I will find that theta is not any function, it is a BV function. So a BV function is a function which is in L1 and such that its distributional derivative is a radon measure. So here, because the Laplacian of h is a radon measure, we will have that the distributional derivative of theta is also a radon measure. So actually, theta being a BV function which takes only plus or minus 1 as values, then it is the indicatrix of a function of a set of finite perimeter. So I call B plus the set where theta is equal to plus 1 and B minus the complement of these sets. And these sets are sets of finite perimeter. So in particular, they have a boundary, or in the sense of geometric measure theory, and they have a normal also in this sense. So we recall that the essential boundary is the set where these limits exist and satisfy the relation, but we will So we can think of the boundary as a smooth boundary for the remaining of the talk, but this is the boundary in the sense of geometric measure theory. And we use that gradient of h is equal to theta gradient of h to see that the normal on the essential boundary of B plus is collinear to gradient of h and gradient of capital H. Okay, but once I have this information, I can describe my measure mu. Why? This is the same computation as I've done in the beginning, because I can write gradient of small h equal plus or minus 1 gradient of capital H. So I use the definition in the sense of distribution of the Laplacian, and I find that my measure is given by this formula. So here I obtain that my measure is concentrated on a curve in a weak sense, because it is only the boundary of a rectifiable set, it's the boundary of a set of finite perimeter. And here I have to subtract the boundary of the ball, the original boundary, because it was introduced artificially. It has no reason to be in the support of the measure mu. We can proceed further by using the theory of sets of finite perimeter in R2. And here, this is very important that I work in R2. So there is a theorem of Fleming and Ambrosio, Caceres, Morel, Masnou, which describes the boundary of such sets. And if I impose some conditions on the, I can find a unique decomposition of the essential boundary of E in a rectifiable Jordan curve and the uniqueness will be given by imposing some condition on these curves. But the fact that they are rectifiable Jordan curves will be very useful for me, because then I can write that the support of mu, which was given by the essential boundary of B plus, is equal to an infinite union of curves, which are simple, connected, and rectifiable. But since I found that the normal to the boundary is collinear to gradient H, it implies that H is constant on each of these curves. So this is just a computation. So H is harmonic, and the support is a union of zero set or level sets of harmonic functions. Now I will use that we know the structure of zero set of harmonic function, and this I mentioned it a little bit in the introduction. So the zero set of an harmonic functions, locally, it is the zero set of the real part of z to the n. So these are n-line intersecting at a point with a prescribed angle of pi over n. And using that, I can deduce that there are only a finite number of such curves. So I have now a picture of the support of my measure around the point 0, and we have an alternance of plus and minus. So the sets where theta is equal to 1 and the set where theta is equal to minus 1. And now, if I take a smaller ball, if I zoom around Z0, I see only one level set, and I can say that this level set is the level set of the harmonic function H. So taking a smaller ball if necessary, we conclude that the support of mu is the zero set of H near Z0. And now to conclude that H is equal to the absolute value of H, or H is equal to minus the absolute value of H, I only have to compute the gradient of H minus theta H in the sense of distribution, and I find this equality. So this concludes the proof of my first result. Now it remains to deal with the case where is in the support of a measure, but it's also a critical point of H. So I didn't state the theorem because it's a little bit more complicated in this case, but we can also describe this situation, and we have to deal with multi-valued harmonic function. For example, a function of this form, r to the 3/2 times cosinus, the absolute value of cosinus 3 theta over 2, satisfies my two equations, and this is the absolute value of a multi-valued harmonic function. I will not do the proof of the result for the magnetic field, because I mentioned first that the non-existent result is due to the Poiseuille formula, and the regularity result follows the same idea. It is more involved, and the way to see that it is more involved is that in the examples we have the example of the abstract problem, which is supported on a set of full Lebesgue measure, but near the points where the gradient of H is different of 0, we can follow the same line as I explained, to have that the measure is supported on lines, and we have then to analyze the set where the gradient of H is 0, and here we find that this is equal to the obstacle problem. And this concludes my talk.
Very nice, thank you.
Thank you. Thank you for that.
Any questions from the audience?